Okay. Okay, thanks very much for the introduction and the invitation. There's a slightly different title. It's changed in the couple months since I submitted the abstract. And these are the old slides from a few weeks ago, so they're not much different from what I was going to do today anyway. So I'm going to tell you all about spanning surfaces for knots in S3. Hopefully a lot of you were watching Hans Boden's talk a little earlier this afternoon, where he did me a great service and introduced a lot of these concepts in a lot more detail than I was going to. Okay, so we're going to be looking at knots in the three sphere. Just to save me some writing extra lines in all the theorems, we're going to exclude the trivial knot. Okay, so nothing applies to the trivial knot. It's always non-trivial. And X is going to be the knot exterior. Okay, so this nice compact three manifold, which has a torus boundary. Now, just sort of for introduction, I want to mention this conjecture, which is still open as of today. And this is called the Neuwirth conjecture. It's sort of a geometric version. There is an algebraic version that was solved by Culler and Shalin using the apolynomial character variety. But the sort of geometric version is still open. And that says, given for any knot in the three sphere, there exists some closed orientable surface F. So like this blue genus 4 surface drawn here. And you can isotope the knot to lie on that surface to satisfy two properties. So one is that the complement of the knot in the surface is connected. And also that complement needs to be essential in the knot exterior. Okay, so incompressible and not boundary parallel. Okay, so here's an example. Here's the knot 949 embedded in a genus 4 Heegard surface such that its complement is connected and essential. So there's been some attempts to try and prove this, and one which seemed like a promising approach was to study spanning surfaces. So Ozawa and Rubinstein made the following conjecture. If you exclude torus knots, well then, which automatically satisfy the Neuwirth conjecture, well then every other knot has, bounds an algebraically essential one-sided spanning surface. Now, if this were true, it would imply the Neuwirth conjecture, because we can take our spanning surface in the knot exterior, we can thicken it up, look at the boundary of that regular neighborhood. We connect the two boundary components by a small annulus, and a knot lives in that annulus. Okay, unfortunately, this conjecture is not true. Okay, so there are knots which do not bound algebraically essential one-sided spanning surfaces. This was shown by Nathan Dunfield. He did a sort of a computer search using spun normal surface theory, and he found 5 examples. They were all twisted torus knots, and they don't bound algebraically essential one-sided spanning surfaces, but nevertheless, these knots do satisfy the Neuwirth conjecture. So let me just remind you, we have to be careful here because we're talking about one-sided surfaces today. So a spanning surface, we're going to say it's algebraically essential if the embedding of that surface into the knot exterior, induces an injective homomorphism between the fundamental groups. That's the algebraically essential. There's also a related notion of being geometrically essential. And so this is if your surface is incompressible and boundary incompressible. I haven't written down the definitions, but you should think of this as meaning your surface cannot be simplified by some sort of surgery along a disk. Now for two-sided surfaces, these two properties are equivalent. So algebraically essential always implies geometrically essential, and the converse is true for a two-sided surface, provided you have to use the loop theorem to prove that. Unfortunately, the loop theorem is not true or fails for one-sided surfaces, and it follows through here it turns out that geometrically essential is a strictly weaker property than being algebraically essential. So I've sketched this, this knot down here, 10, 124. I've shaded one of its checkerboard surfaces. And this is an example of it's a once punctured Klein bottle. And that's a surface which is geometrically essential, but is not algebraically essential. There's some sort of a singular compressing disk for it. And the other thing we need to be careful with one-sided surfaces is often when we're studying two-sided surfaces, we prove that they're incompressible. And then in an irreducible three-manifold, we automatically get that they are boundary incompressible. That result is not true for one-sided surfaces with a single boundary component. Okay, so for spanning surfaces, they can be incompressible, but they can fail to be boundary incompressible. So this conjecture, the previous conjecture of Ozawa and Rubinstein was false, but they also made another one. It had also been asked by Ichihara, Otugi, and Teragaido as a question earlier. And that was whether does every knot in the three sphere are bounded geometrically essential one-sided spanning surface. Okay, so this one is open. Dunfield's counterexamples don't say anything about this conjecture because sort of he was just looking through like boundary slopes that correspond to two-sided surfaces. And this one's still open. So it has been proven for a lot of knots. In particular, it's known for alternating knots, crosscat number 2, so they're knots that bound once punctured Klein bottles. It's true for torus knots, it's true for Montesinos knots, and a couple other classes there. But it's certainly not known for all knots, and maybe the sort of outstanding open case at the moment is trying to prove this for positive knots. Okay, so many of those knots, those counterexamples that Dunfield found were indeed positive. But maybe I sort of think that geometrically essential is not quite the right notion if we're trying to understand spanning surfaces. Because there's this other complication in that if you do a boundary compression of a spanning surface, you do not necessarily get another spanning surface back. So what can happen is your boundary compressing disk kind of winds longitudinally around the knot, and then when you compress, you can end up with a surface at a non-integral slope. So there's sort of a slightly better notion. This is due to Adams and Kindred, and this is what's called a meridionally essential surface. So the definition here for a meridional compressing disk, so we are only interested now in a special type of boundary compression. So D here is my compressing disk. Its boundary decomposes into two arcs. One of them is green here. It lies on the spanning surface. The other one, red, beta, it lies in the boundary, the torus boundary of our knot exterior. And then if we look at these particular curves on this boundary torus, there's a circle coming from the boundary of the spanning surface, it's in green, and there's this arc beta coming from part of this boundary compressing disk. Now, abstractly, this graph is a theta graph. It has sort of two cycles, and then the condition is if one of those two cycles is isotopic to a meridian of the boundary torus, then this is a meridional, we call this a meridional boundary compressing disk. And the advantage of this is if you do a boundary compression along a meridional boundary compressing disk, a spanning surface will compress to another spanning surface. So you guarantee that you stay within the class of spanning surfaces that we're interested in. So then the obvious definitions from that, a spanning surface is meridionally boundary compressible if there are no meridional boundary compressing disks. And a spanning surface is meridionally essential if it is both incompressible and in the geometric sense, and meridionally boundary incompressible. Okay, so you should think of this is a spanning surface which cannot be simplified by surgery along a disk to another spanning surface. Okay, so somehow they're sort of the simplest, topologically the simplest spanning surfaces. And so then we make the sort of obvious conjecture. We've weakened the condition. We couldn't really say much new about the conjecture about geometrically essential spanning surfaces. So we make this conjecture. I'm going to call it conjecture star so I can continue to refer back to it through the talk. But that says that for any knot in the, or any non-trivial knot in the three sphere, it bounds a meridianally essential one-sided spanning surface. Okay, so I'm not going to prove this today, but I am going to show that we can make a lot more progress with this conjecture than with the previous ones. Okay, so let's forget about these technical conditions, meridianally essential for a while, and let's just think about all spanning surfaces for a knot. And so this is what I would call the geography problem for spanning surfaces in the three sphere. And so that says determine all pairs of here, S is the slope, B1 is the first Betti number. I'll explain in a moment, remind you what those are. Which pairs of these integers can be realized by a spanning surface for a given knot? Okay, so there's maybe geography problems are not so common in three manifold topology, but certainly in four manifold topology, there are some quite famous geography problems. The sort of most closely related one to this is you ask the same question that for surfaces in the four ball. And so there's been some nice recent work on this by Samantha Allen. Of course, that's four-dimensional topology. It's much harder. Our version is much easier, but still interesting, I think. There's also some other geography problems in four manifolds, like, for example, complex surfaces. You might want to ask, like, which pairs of first Chern number squared and second Chern number can be realized by surfaces. This is like related to the 11/8 conjecture. There's a lot of sort of these geography type problems in four manifolds. But we're interested in this one, which is in three manifolds. Okay, so the first Betti number of the surface, it's the rank of the first homology group. For a spanning surface, that's just one minus its Euler characteristic. And you can think of that as the minimal number of arcs you need to cut along to decompose your surface into a connected disk. And then the slope, this other invariant we're looking at, well, for any properly embedded surface, it's either a rational number or it's an infinity. And it comes from looking at the class of the boundary of that surface, first homology class in the first homology of the boundary torus. Okay, so that has a basis given by this canonical meridian mu, canonical longitude lambda, and then these integral coefficients P and Q. They describe the slope. Now, if we have a spanning surface, then it just wraps once longitudinally along the knot. So Q is always 1. And furthermore, P must be even. This is because this class must also be 0 in the first homology of the knot exterior with Z mod 2Z coefficients. Okay, so that forces P to be even. And so our slope of our spanning surface must be an even integer. Okay, so now related to this geography problem, there's sort of some big theory which we can apply to narrow this space down. Immediately, the first result is due to Whitney, and this is really about surfaces in the four ball or the four sphere. Has this corollary for the surfaces that we're studying in the three sphere, and that is that the first Betti number of our spanning surface must have the same parity as half its slope. So that immediately gets rid of half of the possible points, which could be realized. And so maybe it's a little bit cheeky, but I also put my initial next to this 80-year-old theorem, but I can also give a new proof of this just using three manifold techniques and nothing to do with four manifolds at all. So you're welcome to ignore that if you, if you don't think I should be doing that. The other big theorem is Gordon and Litherland's theorem. This was mentioned by Hans earlier. But one particular, and he also told us a lot about what signature is. I wasn't going to, so it was good he went before me. And so one corollary of their result is that if you have a spanning surface, small sigma is the signature, then, well, the first Betti number of that surface has to be at least the absolute value of half the slope of the surface plus the signature. So then for this geography problem, we might like to try and plot the possible points. So S and B1 are integer valued invariants. So it could be any points on sort of the standard lattice in the plane. Whitney's result gets rid of all these half these points. There's sort of like missing points here. And the Gordon-Litherland result tells us that the only points that can be realized are the ones that lie in this cone, which is based on at B1, 0 and the slope -2 times the signature. Okay, so then the question is for any particular knot, not all of these are going to be realized. And we have to sort of determine like which ones can and can't from this point. Another interesting invariant that is helpful here is what's called the spanning surface defect. So this was named by Ito, but it was something I'd been thinking about in my thesis. And so this is an invariant of a knot. You take any two spanning surfaces and you minimize the following quantity over for any pair of spanning surfaces. So it's the sums of their first Betti numbers minus half the difference in their slopes. And then you divide it by 2. This will end up being an integer. And this, you should think of this is measuring how far this knot is from being alternating. So it's a theorem of mine and also Josh Green, that this defect is 0 if and only if your knot is alternating. And then as this defect increases, you sort of can think of it as being further and further from being alternating. What it really is it's the minimal genus of a projection surface that your knot can be made alternating on, but where that projection surface doesn't have to be a Heegard surface, it doesn't have to be embedded, it doesn't even have to be orientable. So it can be a bit of a mess, but in some way it's just measuring how close you are from being alternating. And then the other things to take note in this space is like what happens if we have a surface and we do a compression. The first Betti number goes down by 2. The slope doesn't change because everything's happening away from the boundary. If we do a meridional boundary compression, then B1 goes down by 1, and the slope changes by plus or minus 2. There's sort of 2 different ways you could possibly do this boundary compression. But going in the other direction is maybe easier to think about. So if we think about the surface, well, we've got 2 sort of checkerboard surfaces here, sigma and sigma prime. If we go and put this little kink into the knot, it's a Reidemeister 1. And then what's happened to the new checkerboard surfaces? Nothing happened to sigma prime, that's just an isotopy. But in sigma double prime, we've added this extra loop. So the first Betti number has gone up by 1, and the slope of that surface has changed by plus or minus 2, depending which way we did this, which Reidemeister 1 move we used. Okay, so you think of this as like the reverse operation of doing a meridional boundary compression. And of course, you should be able to see there is a meridional boundary compression that goes back in the opposite direction here. Okay, so let's do some actual examples. What does this space of spanning surfaces look like? So here's maybe the first, or maybe the first one I think is interesting, which is also complicated enough to sort of show some of the features. So this is the knot 6-2. It's a 6 crossing alternating knot. The first thing we draw is we draw this Gordon-Litherland cone. So this is sort of indicated in these dotted red lines, you can perhaps see. And then we see surfaces on those extreme rays. So if we look at those brown dots on those 2 red extreme rays, they correspond to the checkerboard surfaces for the reduced alternating diagram. Okay, and the fact that it's alternating, the defect is 0. We do see surfaces on both those extreme rays. And then from those points, we can build everything in sort of the cone above those just by applying these like Reidemeister 1 type moves. Okay. There's also 2 other meridionally essential surfaces in this case. There's one here at slope 2 and B1 is 3. There's also one at slope 0, B1 is 4. That happens to be the Seifert surface. That's a two-sided surface there. But there are also one-sided surfaces at those points. So sort of the idea is if you can understand these meridianally essential surfaces, you can understand the entire geography problem, because every other point sort of away from those can be realized just by these sort of stabilizations, these Reidemeister-1 moves to move about in this space. Okay, I'll give you another example. So here's a non-alternating knot. This is a torus knot. It's the one I drew right at the start of today. And now you'll notice that it's non-alternating. So the defect is 1. This means that there can't be surfaces on both of these extreme red rays coming from the Gordon-Litherland cone. On one side or the other, we must be pushed in by sort of like 1 unit, okay? So we then get this green dotted line, which is maybe you think of like the defect cone, but its apex is now at where B1 is 1. Okay, so now everything's constrained to lie in the smaller cone because the knot is non-alternating. And now there's only 2 meridianally essential surfaces here. One's the Seifert surface. The other one is a less known spanning surface. It is the one I sketched earlier today. And I've been calling them the Pterygido surfaces because he was studying sort of the cross-cap numbers of torus knots, and these are the ones that realize it. But in particular, this is a surface that's not algebraically essential, but is geometrically and meridianally essential. Okay, so there's sort of, I mean, I feel like maybe I haven't seen this geography problem written down in such words before. Maybe that's new to what I'm doing, but there has been related work that does answer this for particular classes of knots. And in particular for alternating knots, this is really probably the paper that has inspired me a lot. This is this paper from Adams and Kindred. And they give a way of understanding essentially this geography problem for all alternating knots. You can start with a reduced alternating diagram. They give some algorithm. You'll get sort of 2 to the number of crossings possible surfaces. And then from those, you build the entire geographical space. Of course, much earlier, a special case of alternating is the 2-bridge or rational knots. Hatcher and Thurston completely understood all surfaces in the complements of such knots. Hatcher and Ertel then extended this to Montesinos knots. There's sort of a little star here because they were sort of focused on the algebraically essential ones, but I think there's enough information contained in that paper if you dig deep enough, and also other people have written follow-up papers where I think if you put it all together, there's enough information to understand this problem for Montesinos knots. And then also in other recent work, I can understand this space completely for torus knots. But then what's sort of newer or more recent is that I actually have a theorem now that there's a normal surface algorithm that can solve this geography problem for any knot. So given any knot, we can just compute this space, all possible points that can be realized, and we would understand all ones that cannot. Okay, and hence there's also an algorithm to compute this defect. So, oh, hang on. Anyway, there was going to be a slide about saying a little bit more about this normal surface algorithm, but that hasn't made it into this version. So maybe I'll just say in words that there's sort of, when you're doing these normal surface algorithms, there's sort of 2 things you need to do. You need to show that the surfaces that you're interested in can be put into normal form. And that's not immediate here because normally with normal surfaces, you want to work with geometrically essential ones. And since we're looking at the meridianally essential ones, they're not necessarily, they cannot necessarily be put into normal form. And it depends on the triangulation. But there's a way of choosing an appropriate triangulation so that such surfaces always can be put into normal form. This is what I call a meridianally zero efficient triangulation. So it's a 1 vertex compact triangulation where the boundary is layered so that one of the edges is isotopic to the meridian. And then the next thing you need to do, you need to show that there's some sort of finite constructible set of surfaces, normal surfaces, that are sort of enough of the surfaces you're interested in appear amongst this finite set. And this uses work of Jaco and Sedgwick. we actually find that if we just look at the fundamental surfaces in the normal surface solution space, then that'll be enough to answer this geography problem. Okay, so let's go back and look at how this applies to conjecture star. It's maybe not a very, it seems like a sort of conjecture that can't really fail. It's kind of, the only way it can fail is if every one-sided, because we start with any one-sided surface bounding your knot, and started doing compressions and meridional boundary compressions, you're just going to get to simpler and simpler spanning surfaces. So the only way it can go wrong is if every single one of these surfaces meridionally boundary compresses to a two-sided spanning surface. Okay, and so then we get this lemma, which helps. If we can find a spanning surface whose first Betti number is strictly less than twice the genus of the knot, plus half the absolute value of its slope, then the knot must satisfy conjecture star. Okay, I don't have to check for meridionally essential surfaces. I don't really have to do anything too technical. I just get this sort of cheap in a way result that satisfies the conjecture. I'll say a little bit on the next slide, sort of explaining that. And then we get the following theorem. So if the defect is strictly less than twice the genus, meaning your knot is sort of close to being alternating relative to what its genus is, or if your knot is M almost positive and M is less than twice the genus. So this again is saying if your knot is close to being positive relative to its Seifert genus. So M almost positive, what that means is you look at it, there's some knot diagram, you put an orientation on it, all the crossings are either positive or negative. M almost positive means that all positive except M of them are negative. Okay, and so in either of these two cases, the knot is going to bound a meridionally essential one-sided spanning surface. And so the first case, and this sort of explains it, if the defect is less than twice the genus, then there must be some surface sitting out in this defect cone, which isn't in this sort of Seifert cone. And so when you compress that, there's sort of this green dot here, this will be a surface that has to be meridionally essential and one-sided. And in the second case, the ones that are close to being positive, what this means, M is measuring how close we are to being positive. If that is less than twice the genus, then there's this line at slope, slope a half. I mean, slope in the sense of the slope of the line, not the slope of the surfaces. So you take your M almost positive diagram, you look at the two checkerboard surfaces. On average, those two surfaces have to lie on this purple line, but that's only on average. And so if you push one off in one direction, the other one has to be pushed off by an equal amount in the other. And nevertheless, at least one of those surfaces must lie on or below this purple line, and hence it can't compress to the Seifert surface. So I think I mentioned that this defect, that includes all the ones that are M almost alternating. And in particular, this means that all knots with at most 12 crossings satisfy conjecture star. Okay, I can't go any further because the knot info only goes up to 12 crossings, but I think these techniques should be enough to push that a little bit further. The other, I was just going to mention, here's a case where this conjecture star is still open, maybe something to think about if someone's interested. These techniques do not work for knots such as have Seifert genus 1, but their free genus is strictly larger. Okay, because in that case, all the surfaces have to live in this Seifert cone. So this could be some sort of a satellite knot, or there are hyperbolic examples with totally knotted genus 1 non-free Seifert surfaces. Okay, so one more example, let's look at these knots of Nathan Dunfield. So he found 5 knots that did not bound algebraically essential spanning surfaces. 4 of them happened to be positive, so they automatically satisfy that previous theorem, and so they must bound meridionally essential spanning surfaces. The 5th one is this twisted torus knot. It's not known to be positive, It certainly doesn't look positive. The naive diagram you would draw here would have something like 262 crossings with about 80 almost positive. But I found a slightly better diagram. This is a braid diagram. You close it up, take the braid closure. This is now 3 almost positive. That's not quite enough to satisfy the conjecture because I don't know the genus. But if we look at these 2 checkerboard surfaces, the shaded one here has slope 110, first Betty number 53. And so it must satisfy conjecture star. But you can notice that there's many obvious compressions and boundary compressions for that surface. So really, the first Betty number should go down a long way if you really wanted to find the minimal such one. Okay, I think I'm about out of time, so maybe I won't say too much about this. There's sort of this geography problem also has some applications to looking at. I don't know, I guess in a way I would say applications to looking at, say, Dane fillings of hyperbolic knots, if you want to understand which fillings contain closed non-orientable surfaces of, say, Euler characteristic -1 or -2. There are some applications. Here's sort of a statement that generalizes a theorem of Ichihara, Otugi, and Teragaido. So there's some examples there. And I'm also thinking about trying to extend this to not spanning surfaces, but just once punctured surfaces in knot complements. And there is sort of, it's not really, this isn't really a planar picture anymore. The right idea is to sort of think about the slopes lying, being organized in a tree. This is this Möbius band tree introduced by Bartolini. And then you'd think about the Betty numbers lying above this tree and thinking about cones over geometrically essential surfaces. And again, there's some small applications to some sort of like Dane filling questions. Okay, so I'll stop there. Thank you.
Okay, thank you very much. Are there any questions? Or Joshua, do you have any possible candidates for counterexamples to your conjecture?
Not really. I mean, I think the closest ones is maybe some of these, maybe like a genus 1 satellite knot with like 0 winding number. Yeah, I don't know if it's going to work or not, but I mean, that's the sort of thing that's like these techniques don't apply to, and is sort of the simplest possibilities I can think of that might, that could give counterexamples.
Mm-hmm.
But so, I want it to be true.
Yeah, but this, your conjecture is, I mean, maybe I didn't understand, but is with the relation with Newell's conjecture?
Yeah, so there's no longer any direct relation, like it neither implies nor is implied by the Neuwirth conjecture. That was more just sort of the motivation and sort of the inspiration to start looking at this. Like people started studying these variations to hope to prove it. And then they were either hard or they were incorrect. And so this is like another variation on the variation. It doesn't really have much to do with it anymore. It's just interesting, like does every knot bound at one of these sort of a topologically interesting one-sided spanning surface.
Okay. Any other questions? Okay, if not, thank you for your talk.
Great, thank you.